behaves like a wave. So the dual nature becomes very obvious when you go down to the very level of minute particles. Well, let's now talk about Schrödinger wave equation. Now, you've got to appreciate one thing. We are taking a big concept of quantum mechanics. There are volumes of books written on it, and I'm going to condense that idea into one of these classes, about roughly 1 hour. So I will simply pick ideas and try to develop the model of the atom from there. Now, Schrödinger wave equation. What is a wave equation? We discussed the wave equations before. For a vibration of the particle, the wave equation tells you where the particle is at a given time. Is that right? In fact, you know that we obtained equations like y as a function of x and t, position and time, equal to a sine kx minus omega t. Do you recognize that equation? Well, that explains the waving part of a particle. Now, can we develop such an equation to describe the electron? And Schrödinger equation is such an equation. Schrödinger's equation gave a much more precise description of the electron's location and energy than Bohr's model. Well, remember, Bohr's model did not give you a clear idea beyond the hydrogen atom. It is the Schrödinger equation came in and described it in much more detail using the quantum model. Now, the wave function for a classical wave traveling with a wavelength lambda and amplitude a, the classical wave is the wave that we have discussed earlier, is this. Psi xt, in place of y, the displacement, I use the letter psi. In fact, that is Schrödinger's notation. Is a sine 2 pi x over lambda minus omega t. Now, this is the same. 2 pi divided by lambda is the wave number k. So a sine kx minus omega t, that is the normal description of a wave we discussed earlier. Now, it is reasonable to assume that this wave function is associated with a particle's energy, which is both kinetic and potential. So this wave function is actually determined by the energy of the particle. The particle, like an electron, has a potential energy because of its position, isn't it? Its potential energy is greater as it's farther away from the nucleus. It has kinetic energy because it has velocity. So this wave function really depends on its potential and kinetic energies. And Schrödinger proposed an equation for the de Broglie matter waves. So the de Broglie matter wave is actually made into more quantized form by Schrödinger equation. And he gave a picture of that wave by the wave function psi. Psi is the wave function which is used in this equation. Now, what is that wave function psi? Very often it remains an enigma for many quantum mechanics students, leave alone students like you who have no idea of quantum mechanics. Now, Schrödinger equation can be written like this. Psi, which is a function of the kinetic and potential energies, equal to E psi. E stands for the total energy. So what it tells you is that the wave function that describes the electron is actually a function of the total energy of the electron. And that can be used to locate. Can we locate precisely where the electron is? That's a different task. Well, if psi represents an electron beam, if we consider an electron beam, then psi squared is proportional to the number of electrons that can be found in a given volume. Now, you notice that we used chi-square. When you square a quantity, a lot of ambiguity can be reduced because all the negative parts will become positive. That's why we square that psi. Now, if there is only one electron, then what does chi-square represent? Chi-square represents the probability of finding the electron at a particular point. That's a positive quantity. So, as far as we are concerned, Schrodinger equation gives you a method of finding the probability of locating an electron at a particular point. Now, you must understand that Bohr's picture of the atom gave you the exact location of the electron, isn't it? We calculated the radius of a Bohr orbit. We know precisely where an electron can be found. But in quantum mechanical model, we cannot precisely determine where the electron can be found. But we can talk about the probability of finding the electron at a point. And chi-squared, which is given by Schrodinger's wave equation, gives you that measure of probability. It is proportional to the probability of finding a particle in space and time. So psi is a function of space and time. Now, that leads us to another important concept in quantum mechanics. You can see I'm picking ideas, putting it all together, which is the Heisenberg uncertainty principle. I'm sure most of you have heard about it. Now, what does the uncertainty mean? Well, do I know exactly if this stick is in front of me? Is there any measure of uncertainty about its position? Well, as far as we are concerned, we would say, no, I know exactly where it is. But when it comes to a particle like an electron, which behaves both like a particle and a wave, it is very difficult to assign a specific position and determine where exactly the particle is. And it is therefore very important to discuss the uncertainty principle. In 1927, German physicist Werner Heisenberg developed what is now known as the Heisenberg uncertainty principle. Now, this hypothesis states that the position and momentum of an electron or any moving particle cannot both be known precisely at the same time. In other words, if I try to measure exactly where the electron is, I lose information about its velocity. If I try to measure precisely the velocity of a moving electron, I lose information about its position. That is what it means. Now, how can that be? Well, remember, electron is such a very minute, tiny particle. If you want to locate a particle, now, how do you locate me? Well, if I turn off this projector, you can see it is the light of the projector that makes you see me. If I turn off this projector now, you will not be able to see me. Look at this. Well, so if I have to locate an electron, I have to project a beam of light onto it. But light consists of this energy package called photons, isn't it? And when these energy packets fall on the electron, they disturb its position. So the very fact that we use a beam of light to illuminate an electron so that we can look at it will change the position of the electron. So when you try to locate it, its position changes. So when you want to measure its location, its velocity changes. When you want to measure its velocity precisely, its location changes. Now, this is where the uncertainty principle is important. We're going to represent delta x to represent the uncertainty in determining the position, and delta p in determining the uncertainty of momentum. That means if I can determine the position precisely, then the uncertainty in the momentum will be very large. If I can determine delta P precisely, then uncertainty in the position will be very large. And Heisenberg expressed this as an equation like this. Delta P times delta X is greater than or equal to h over 2 pi. Now that means the minimum value of this, the minimum value of delta P over delta P times delta X equal to h over 2 pi. So if I ask you to find the minimum uncertainty, I can change this inequality to an equation. All right. Now, this can also be written in terms of the energy and time like this. Delta E times delta T is greater than or equal to h over 2 pi. Well, we will be using mostly this form of the uncertainty principle. Well, let's do a